Okay, so let's take a look at the schedule now. All right, so next up on the grading is homework 3, by the way. That's next step in the grading, by the way. All right, now, so today is November 30th. All right, tomorrow's the 1st. If you're paying rent, the rent check's tomorrow, right? Okay, and if you look at these we have 3 days of material, right? 3 sessions of material, right? Lessons 33 through 43, a lot of it, that's 11 lessons, all right? So it's very dense, okay? So a lot of stuff to talk about. Although we'll have time to talk about it, right? We'll have a couple of sessions to talk about all this, right? And the homework for this will be due, okay, Tuesday, December 15th, which is technically after the end, but that is following the policy, right? One day after the corresponding homework session. So the Monday, December 14th here really is the last day of class, but as usual, the due date will be the following day, midnight of the following day, Tuesday, December 15th, covering these 11 lessons. The homework isn't so much that long. It's not super, super long, but there are a lot of dense ideas there. Okay, so it's good that we have a couple of days to discuss it. All right, so any questions before we begin the videos? And like I said, the material of this last part is pretty dense on hypothesis testing. So there may be times when I might want to pause the video. Feel free to ask questions in chat, okay? Lots of ideas here. So without further ado, let's go ahead and start. We're doing lessons 33 and 34 today. We're starting part 5 of the class, the last part. Okay, questions in chat.
Hi, everyone. Let's start lesson 33 on hypothesis testing, setups, decisions, and conclusions. What is the structure of a hypothesis test? Let's begin, not surprisingly, with a setup, setting up a hypothesis test. And we have seen the cast of characters. The setup for a hypothesis test includes a null hypothesis, denoted by H naught or H sub 0. The null hypothesis is an assumption that calculations are based on. We can compute probabilities and test statistics on this assumption. The classic null hypothesis we used back before in previous lessons, the coin is fair. Classic null hypothesis. Or it could be something like the mean of the test scores in a class is 70 points, something like that. Something that we can base calculations on. Now, we live in a world where either the null hypothesis is true or the alternative hypothesis is true, H sub 1 or maybe H sub A. Again, the alternative hypothesis is everything that the null hypothesis is not. So for example here, let's see. The alternative may say that the coin is not fair or that the coin is biased. Or for the second one over here, the alternative could say that the mean of test scores, let's say, is not, I'll put not in capital letters, is not 70 points. We live in a world where either the null hypothesis is true or the alternative hypothesis is true. And then there is a claim. This is the first time that I'm really introducing this, really. I've mentioned it before. The idea of a claim. And this depends on the wording of the given problem. I'm going to say in a hypothesis test problem, the claim is da-da-da, something like that. And depending on the wording, either the null hypothesis or the alternative hypothesis could be the claim. And you have to figure out when it's the null, when the claim is the null, and when the claim is the alternative. Sometimes it's one, sometimes it's the other, based on the wording of the problem. And that's the claim that we're testing with a hypothesis test. So we're going to make a decision on what to do with the null, and we're going to make a conclusion. The conclusion of the test will eventually be worded with respect to this claim. So our decision is going to be that we reject or not reject the null, and then the conclusion will be worded with respect to the claim, that David's coin is fair or not fair. And then, we've seen this before, a significance level alpha. Before I said this was the third ingredient, here it's fourth in my list. It's the third ingredient to a hypothesis test, fourth if you include the claim in the wording. All right, so alpha represents the threshold for what it means for sample results to be too unusual for the null hypothesis to survive. Under the null. Remember, we make calculations under the null. And remember the deal. Whatever your value for alpha is, it's usually 0.05, but it could be, say, 0.01 or 0.10. But whatever alpha is, remember, what's the relationship between the p-value and alpha? What was the rhyme? P-value is low, the null must go, as in go away. So if the p-value is down here below alpha, remember before our little game, let's say that we flip a fair coin 7 or 8 times and it comes up heads all 7 or 8 times, then a lot of those judges are going to say, I don't buy that. The p-value is too low. The probability of what we see is too low. Or remember the p-value is like a tail thing, right? Could be like a 1-tail or 2-tail p-value, say, but the probability of getting something at least as unusual as what we've seen. That p-value is so low, the null must go away, like 7 out of 7 heads, for example, if alpha was like 0.1. All right. Now, over here, remember we talked about the null saying that, oh, the coin could be fair, or the mean of the test scores was 70 points, right? But remember, when we said that the coin is fair, that corresponded to the idea that P, the probability that the coin comes up heads, let's say, was 0.5. Down here, we're saying that the mean mu is 70 points. So often the null hypothesis says that one of these population parameters is equal to some value. That's your typical null hypothesis. The null hypothesis and the alternative hypothesis often say something about the value of a population parameter, possibly a population mean, mu, p, a population probability or proportion, sigma, a population standard deviation, or sigma squared, a population variance. Later on, we will talk about other types of null hypotheses, but the basic old school type of null hypothesis would say the value of a population parameter is some number. The mean is 70 points. P is 0.5, something like that. Okay, now the null hypothesis often states that a population parameter takes on a particular value, and informally, we're going to call this the reference value. That's not an official term, it's just my term. So for example, in the case where the coin is fair, all right, P equals 0.5, 0.5 is your reference value. In the case where mu, the mean is 70 points, all right, 70 points is our reference value. The null says the mean equals 70 points. Okay, the alternative then states that the population parameter, I'll just move this down. The alternative then states that the population parameter does not take on this value. And this is the setup for a two-tailed test. Okay, so that would be like P is not 0.5, or the mean is not 70 points. That's going to be the setup for a two-tailed test. Okay, so let's talk about this. And then later on, we'll talk about other types of tests. But let's talk about a two-tailed test. Example 1, the magician's coin. We want to test the claim that, and you might even want to circle this, a magician's coin is fair at the 0.05 significance level. I'll star this. If you're rushing at the end of an exam and you have to write the claim really quickly, maybe put a star there. Okay, it's like copy paste. We want to test this claim that David's coin.
I could have made this easier. Really, the claim is that a magician's coin is fair. A magician's coin is fair. I may have corrected this later in the video. All right. But that's the claim.
Is fair at the 0.05 significance level. Whoa, whoa, whoa. I'm sorry. I made this too big.
Yeah, I just noticed that. Okay.
The magician's coin is fair. A magician's coin is fair. All right. It's a small claim. Okay, we want to test the claim that a magician's coin is fair. That's the claim. That's all it is at the 0.05 significance level. All right. So this here is, what's the symbol? Fishy. Alpha. It's the first letter of the Greek alphabet. It's fishy. Alpha is 0.05, which is standard. Okay, so we could let P be the probability that the coin comes up heads. I guess there are basically two parameters you could realistically set up. Either the probability the coin comes up heads or the probability the coin comes up tails. Let's let the P be the probability the coin comes up heads. And here's a setup for this two-tailed test. The null hypothesis says that P equals 1/2. Remember, the notion that the magician's coin is fair, that corresponds to P being equal 1/2. I'm going to erase this. The notion that the coin is fair, that corresponds to P equaling 1/2. And it turns out that's the claim. Based on the wording of the problem, right? We want to test the claim that a magician's coin is fair. The claim is that the magician's coin is fair. Bear in mind, the wording could have just as easily said that the claim was the magician's coin is unfair. And by the way, the alternative is the one that says that. The alternative hypothesis would then say that the coin is unfair or biased. That is, P is not 1/2, meaning that P could either be less than 1/2 or greater than 1/2. Maybe it's biased towards heads or tails. And remember, alpha was 0.05. That's given in the problem. So that's the setup for a two-tailed test. And then later on, we'll talk about methods by which we can come up with a decision as to whether or not to reject the null, and then how to write out the final conclusion. But for right now, we're going to write down the 3 key ingredients based on maybe the 4th ingredient in the wording. Write down the null, write down the alternative, write down alpha. And the way that you write these down depends on what the claim is. The claim is that the magician's coin is fair. That is, P equals 1/2, and that's the claim. Now, the reason why this is the null hypothesis is that if you have a statement that says that a parameter like P equals a value, that's going to be the null. And then the alternative will be P maybe is not equal to that value. Alpha is given. Okay, so next video, we're going to talk about one-tailed tests, right-tailed tests, and left-tailed tests, where these look a bit different. Next time.
Any questions thus far? Because remember, you want to make sure you get these foundations right. Otherwise, the later videos get confusing. You see it gets very packed in at some point. Any questions? Okay, please let me know if you have any questions about these fundamentals, because otherwise the massive videos won't make sense. All right, let's go on.
Hi, everyone. We've talked about two-tailed tests here in the context of the magician's coin. Let's continue with the magician's coin and now talk about right-tailed tests and left-tailed tests. So in a typical right-tailed test, the alternative hypothesis, bear in mind that the tails correspond to the alternative hypothesis, okay? For example, in the two-tailed test, right? Imagine that this is a number line for P, okay? Then in the two-tailed test, the alternative hypothesis favored both the right tail, the higher values of P, and this left tail, the lower values of P, away from 0.5. So in a two-tailed test, the alternative favored both the right tail and the left tail on this P number line. Now, in a right-tailed test, the alternative hypothesis favors the right tail. And remember, the tail corresponds to the alternative hypothesis. Okay, we have a right-tailed test here. Here, the alternative states that the value of a population parameter is greater than a particular reference value. Again, think of the alternative as favoring the right tail of the real number line, corresponding to greater values of the parameter. So in our example, well, the magician's coin example, we want to test the claim that a magician's coin is biased towards heads. Biased towards heads at the 0.01 significance level. So we can let P be the probability that the coin comes up heads, as usual. And here is a possible setup for this right tail test. It's the one that we typically write up. So the idea of being biased towards heads, that means that the probability of getting a head will be greater than 1/2. So the claim is that the magician's coin is biased towards heads. And we should indicate which is the claim, the null or the alternative. Up here in the prior example, the null was the claim when we claimed that the magician's coin is fair. Here, the alternative hypothesis is the claim. Again, the claim could be the null hypothesis or the alternative hypothesis, depending on the wording of the problem. And alpha is 0.01. That's very straightforward. No tricks there. Now, again, the alternative says that P is greater than 1/2. And remember, the null hypothesis and the alternative hypothesis basically divide up the world. We live in a world where either the null hypothesis is true or the alternative hypothesis is true. Now, the alternative hypothesis says that P is greater than 1/2. The null hypothesis would then have to say that P is less than or equal to 1/2. Use a different color here, green. The null says that P is less than or equal to 1/2. Because again, we live in a world where either the null is true or the alternative is true. Now, the idea of being biased towards heads, that corresponds to a tail. On this P number line, the bias towards heads corresponds to the right tail. Higher values of P. The null hypothesis always contains the case of equality. So over here, P is greater than 1/2, that's the claim. P is less than or equal to 1/2, that's the null. And the null hypothesis, whenever you have this reference value involved, the null always contains the case of equality. Now, as you saw me do here, in this example, it may be easier to set up the alternative hypothesis first, because the claim here, the bias towards heads, that implies a tail, that corresponds to the alternative hypothesis. And that's fine. You can write the alternative hypothesis first. Okay? And then use the fact that the null is everything that the alternative is not. Now, an easier way to look at this, it is conventional that instead of writing P as less than or equal to 1/2, we simply write P equals 1/2. It's a kind of shorthand almost. Right. But really, it means that P is less than or equal to 1/2. So this really means that. For convenience, we often write this, and it is conventional to write this null hypothesis as P equals 1/2. The alternative is the same as before. P is greater than 1/2, which is still the claim. Okay, the same. So books almost always write P equals 1/2. And again, absorbed in this is the case of P being less than 1/2. One reason why this is convenient to do is that, well, for one thing, the equal sign is more familiar to us, but also remember, the null hypothesis is the assumption that calculations are based on. So in that sense, when we say that we're performing calculations under the null, if we just say, okay, let's assume P equals 1/2, then it's more straightforward to work calculations based on that assumption. Although it also includes the cases where P is less than 1/2. Basically, P equals 1/2 represents the boundary case. Okay, it's the case that's closest to the alternative without being the alternative. It's like the boundary case. Again, when we calculate, it's easier to assume that P is straight up equal to 1/2. I should write this in green. The green is the null here, right? It's easier to say that P equals 1/2, although technically, in fact, it really means that. Okay. Again, think of 1/2 as the borderline case of P being less than or equal to 1/2. So that was the deal with a right-tailed test. With a left-tailed test, well, no surprise there. In a typical left-tailed test, the alternative states that the value of the population parameter is less than a particular reference value. So in a left-tailed test, the alternative looks towards the left tail. Right now, we're looking at values for P, but this could be a number line for mu or sigma squared, for example. In example 3, we want to test the claim that a magician's coin is biased towards tails at the 0.10 significance level. Now still, even though we're talking about tails here, we could still let P be the probability the coin comes up heads. That's okay. And here's a possible setup for the left-tailed test. Again, it might be easier to set up the alternative first. The claim is that the bias is towards tails, which means that the probability that the coin comes up heads would be less than 1/2. A bias against heads and towards tails. So again, it's easier to write the alternative in this case. The alternative would not include the case of equality. This alternative favors a tail. Now over here, well, here, I guess you could say in the end, this also favors a tail, but it's not the tail that's specified in the claim here. All right, now, the thing is, it's a left-tailed test because the alternative favors the left tail. The alternative favors the left tail, so that's why it's a left-tailed test. It's a left-tailed test because the alternative favors the left tail of this number line for P. The null favors the right tail in the case of equality. And again, it may be easier to set up the alternative first, that was the claim, and then use the fact that the null is everything that the alternative is not. So here, P is greater than or equal to 1/2 would be the null. But once again, it's conventional to write, instead of is greater than or equal to, it's conventional to write a straight up equal sign. P equals 1/2. It's very conventional for books to write that, the borderline case. And this assumes that. So really the null includes the case of P being greater than 1/2, but we're focusing on the boundary case because that's what we base calculations on. Okay, so again, remember that the alternative tells us what kind of test we have. Here, we have a left-tailed test. It favors lesser values for P. And yes, it is typically the case that in a one-tailed test, the claim would correspond to the alternative because that's the case where it's easier to set up the alternative claim. But not always. In the usual case, yes. In a one-tailed test, the claim often refers to the alternative, but not always. And again, right-tailed test and left-tailed test are two types of one-tailed tests, which means that the alternative favors more one tail as opposed to the other. And for both one-tailed and two-tailed tests, the null includes the case of equality, which is a reason why for the null hypothesis, you almost always see written or typed the parameter equals the reference value, in this case, 1/2. Now, in principle, a null hypothesis can consist of any one of these signs, an equal sign, or these inequality signs, but for all practical purposes, we tend to write that. Okay, next up, how do you decide whether to reject the null or not? Next time.
All right. Once again, and I'll try to pause more between videos. Questions? Any questions? I don't want to rush. Any questions? Feel free to ask questions in chat at any time. Any questions? Okay. All right. Hi, everyone. Let's talk about decisions, how to decide to reject the null or not, and writing down
final conclusions relative to the claim or in terms of the claim so that a layperson can read it. Someone who hasn't taken statistics. Shame on them. Okay, in a hypothesis test, we decide to do one of the following. Literally, we decide. We decide to do one of the following based on our sample results. We're either going to reject the null, in which case we accept the alternative. If we reject the idea that the coin is fair, we then accept the idea that the coin is biased or unfair. Or we do not reject the null. But remember, we never accept the null. We can accept the alternative, but we never accept the null. It's right here. We sometimes accept the alternative, but we never accept the null. The null never gets love. Because remember, let's say that the coin comes up heads 50 times in 100 flips. Even then, you would not accept a null hypothesis that says that the coin is fair because there's still vulnerability to sampling error. It's still quite possible that the coin was actually a 0.51, like a 51% heads coin, and the 50 heads may have been due to sampling error. So even if you get 50 heads in 100 flips, you never affirmatively accept that the coin is fair, that the null is true. You never say innocent at the end of a jury trial. You might presume innocence, and we should, right? We assume the null is true as we make calculations, but we never say in the end innocent or the null is true at the end because there's still vulnerability to sampling error. If we don't reject the null, it basically means that we can chalk things up to sampling error. Okay. Based on our decision, we write a conclusion relative to the claim or in terms of the claim. The conclusion may be written in two parts, and this procedure, I guess, is written and summarized in these tables. Now, some books have a fancy flow chart, but it's actually much simpler than that. This might seem kind of silly to you, but it's this basically mix-match thing where, okay, if you reject the null, you start the sentence one way. If you don't reject the null, you start the sentence another way. If the claim was the null hypothesis, you end the sentence one way. If the alternative was the claim, you end the sentence another way. Again, it seems kind of hokey. It seems silly, but it works, folks. It works. All right. So let's say you reject the null. You get, for example, 99 heads in 100 flips, and the null says the coin is fair, right? Then it's highly likely that you're going to reject the null. That's a strong result. When you reject the null, that's a strong result. That's like saying guilty. You are guilty. You're going up the river. You're guilty. Okay, that's a strong result or a statistically significant result, which means there is sufficient evidence to say something. If you reject the null, if you reject the null, there is sufficient evidence to say something. Whereas, if you do not reject the null, that's a weak result, that's flaky, that's like not guilty. Well, I don't know, you can be innocent or guilty, but we just don't have enough evidence yet. Seriously, we don't have enough evidence yet. There is insufficient evidence to say something. Statistically insignificant. That would be like if the null says the coin is fair and you get 51 heads in 100 flips. That's a weak result. There's some evidence against the idea of a fair coin, but not very much, right? A fair coin could easily come up 51 heads in 100 flips. Okay. Now, the rest of the sentence, the rest of the final conclusion for the layperson is written based on which hypothesis is the claim. If the null hypothesis was the claim, then it's like a jury trial. The null is on trial, and we're wondering if we can convict or reject it, right? So if the claim is David's claim, my coin is fair. So we put the coin on trial. We put George Washington or maybe David's mom on the coin on trial, okay? And we ask, can we convict this coin? Can we reject the idea that that coin is fair? The null is on trial. So we're weighing evidence against the claim. That stating the claim. For example, the coin is fair. So there's either sufficient or insufficient evidence against the claim. We're weighing evidence. How do we weigh evidence? We're weighing evidence against the claim if the null is the claim, because we're putting the null on trial and we're weighing the evidence against the null claim. If there's enough evidence, bye-bye. All right. Now, if the alternative is the claim, then we can think of the alternative hypothesis as a research hypothesis. Can we publish something interesting? So for example, does this drug work? That would normally correspond to the alternative hypothesis, right? For example, if you have a drug that lowers cholesterol or that lowers blood sugar or that raises some level of hormone, for example, right? So in a research hypothesis, you're usually weighing evidence for a tail, basically, for a tail. The null would say, there's no impact, or the two groups are similar, something like that. Okay, the null's kind of flaky, but the alternative is saying, hey, there's a result, our drug works. Our drug works, this procedure is effective, something like that. Or on the other hand, this medicine kills, it could go that way. So if the alternative is the claim, we think of it as a research hypothesis, and we wonder, can we prove it? Again, if the null is the claim, we ask, can we convict or reject it? If the alternative is the claim, we ask, can we prove it in the affirmative? So we're weighing evidence for the claim or in support of the claim, that da-da-da. So for example, the alternative claim may be the coin is biased, or perhaps more interestingly, the drug works in the sense that cholesterol, bad cholesterol is lowered, something like that, right? Can we prove that this drug works to lower cholesterol? Okay, we're going to weigh evidence for the claim that the drug works to reduce cholesterol, bad cholesterol. Okay, so we're going to get right to it, and we're going to use these pieces as we conduct hypothesis tests. Starting with lesson 34, we're going to start with hypothesis test for P, and we're going to test this hypothesis. Is the coin fair? That's next time.
Any questions thus far? Now, I know you may have a hard time believing this, but this sort of Mad Libs thing, this mixed match thing really works. It's a matter of having confidence and faith in the scheme when you apply it. I know you might have to kind of wrap your head around it, but any questions? And by the way, based on the news reports, all these vaccines seem to be very effective, right? We're looking at 94, 95% effectiveness. And this is the kind of thing they've been doing. They do these kinds of things in their official studies. All right, questions? All right.
Hi, everyone. I hope you're not done with this. Is the coin fair? Lesson 34, hypothesis test for P, which, remember, is a population proportion or probability. So a politician would care about share of the vote, for example. All right, let's do hypothesis tests for P, lesson 34. For a fixed sample size n, we assume that we have a binomial experiment. So you remember that. We flip a fair coin 100 times, or in a poll, we randomly sample 1,000 people. We can assume independence because of the sampling rule, and so forth. If X is the number of successes, like the number of heads or the number of people who are for Senator Smith, then we can assume that X has a binomial distribution, NP. So N is the fixed sample size. That's no surprise. But now P is unknown. Okay, we don't know truly what Senator Smith is going to get. We don't know truly what this coin really is or does, unless we do a physics analysis or something. All right, so you take this coin, this magician's coin, and you flip it a bunch of times. You flip it n times, so your sample size is n. So what's your best point estimate? What's your best point estimate? The sample proportion p hat, which is the number of heads or the number of successes over the number of flips, the sample size. So the number of successes over the sample size or the number of trials. Okay. So for example, if you get 51 heads in 100 flips, then the sample proportion p hat is given by 51 over 100, 0.51. And that's our best guess for a p, the true probability of heads on this coin. All right, now, remember that for a normal approximation, we need to verify that NP is at least 5 and NQ is at least 5 under the null. So remember, the null hypothesis is going to say that P takes on a particular value. P takes on a particular value, and therefore Q takes on the complement. So under the null, see, under the assumption the null is true, we have values for P and Q. So for example, if the null says the coin is fair, then we're assuming P is 0.5, and therefore Q is also 0.5. 1 minus 0.5 is 0.5. So these values would go in here. And N would be the number of flips. So remember, there is a bit of arrogance here. It's kind of like the presumption of innocence. We're assuming for now the null is true. So we're assuming for now that we have, in this case, a fair coin. Again, we will temporarily assume that the null is true. So we will use the reference value for P, like the 0.5 here, or 1/2, the reference value for P, and the corresponding value for Q, which is the complement, 1 minus P, when we do this verification. And also later on, we'll use these values for P and Q. For convenience, we will not be using continuity corrections, although we could use them to be more accurate. Okay. So now, before we get to the idea of a p-value, we're going to talk about test statistics. And a test statistic is a single number that we get based on the sample and what we're doing with our test, right? What the null says, what the alternative says. We're going to use the Z-Test Statistic as a way of summarizing the data relative to what we're doing, right? What the hypothesis test is. In particular, what's the hypothesized value for P, and therefore the hypothesized value for Q under the null. So all of these are under the null. I'll do this. So we're going to plug in values for P over here, and Q under the null. Remember, for the time being, we're going to assume that the null is true. And remember, the null, in this lesson, the null is saying something like P is 0.5, for example. All right. So before we get to p-value, we're going to get the test statistic, which is a number that summarizes the results from a sample relative to these hypothesized values under the null. Okay, so it's going to help us decide whether or not to reject the null hypothesis. And we're going to use distributions like Z, like T, like chi-square to help us calculate the test statistic and decide what to do about the null. So this is a number that's going to help us figure out what to do about the null. And eventually the p-value may be wrapped up in this as well. So here is the Z-Test Statistic for test for P. Here's the formula.
I don't know what happened to me here. I think I had to pick something up.
So now, when does this formula make sense? So let X be the number of successes in n trials of a random variable. If X has a binomial distribution, NP, then X has this distribution. Okay, now this is theory, so folks, yeah, don't freak out too much. I want to explain why it is that this formula makes sense. I'll make this quick. So remember, X has a binomial distribution. This is a distribution for like the number of heads on, say, 100 flips of a fair coin. We're assuming for now the coin is fair. P hat is X over N, right? You take the number of heads divided by the number of flips. That gets you the sample proportion. And it has this distribution where you divide these guys, mean and standard dev, by N. So then we get these values for the mean and standard deviation for our normal approximation, all right? And then you can go through the Z formula. You go through the Z formula, all right? Plug in these values for the mean and the standard deviation, all right? We're considering the number of heads, for example, all right? If you divide the top and the bottom by N, you have things in terms of proportions, right? Again, we're using the fact that P hat is X over N, number of successes over number of trials. There you go. So it comes through from the algebra. Don't freak out too much about this. All right. Coin examples. Example 1, the magician's coin. And also we're going to explain why we never accept the null hypothesis. This will be a two-tailed test, and we're going to revisit a prior lesson. Okay, so as in that lesson 33, example 1, we want to test the claim that a magician's coin is fair at the 0.05 significance level. Let P be the probability that the coin comes up heads. Here's the setup for this two-tailed test. All right, so the magician's coin is fair. Test the claim that a magician's coin is fair. Okay, like this. A magician's coin is fair. All right, so that's going to be our claim. It's already bold-faced there. A magician's coin is fair. All right, so that means that the claim is that P, the probability of heads, is 1/2 or 0.5. So this is going to be the claim based on the wording. Fair coin. P equals 1/2. Because this is the case of equality, where P equals the reference value, that's going to correspond to the null hypothesis. The assumption is that if the claim corresponds to just the case of equality, then the alternative here suggests a two-tailed test. P is not 1/2 or 0.5. And we have a two-tailed test because the alternative favors both high values and low values, both the right tail and the left tail, for this P number line. Alpha is a significance level is given, 0.05. All right. Now remember, you're not supposed to cheat. Do not gather sample data until after the setup has been determined. So remember, all of this over here has to be determined before you flip that coin, all right? Don't touch that coin. Don't touch that coin until you set up this experiment and you set up this hypothesis test. Now, at this point, we gather sample data. That means flip the coin. Let's say the coin is flipped 100 times and it comes up heads 51 times. All right. Now the rounding instructions will vary, but here we're going to round off to 4 significant digits, except we're going to round off the Z-Test statistic to 2 decimal places. It's usually standard that the Z-Test statistic would be rounded to 2 decimal places because of tables and some software. So the sample size, N equals 100 coin flips. The number of successes, X, is 51 heads. The sample proportion, our point estimate for the true probability of heads, is X over N, 51 over 100, or 0.5100. 0.5100. 4 significant digits. And then we're going to verify that normal approximations are appropriate in this problem. So under the null, right, we have to show that NP is at least 5. And NQ is at least 5.
And by the way, one comment, I don't know why I made a big deal about the 0.5100. If you put 0.51, that's exact. That's fine. I don't know why I pushed that.
Now, I know before that we used to take the number of successes, but over here, look, this is not NP hat or X. This is NP. It's under the null. So you do not take the 51 up here. N is 100. P is 1/2 under the null, right? 100 times a half is 50. 50 is at least 5. Check. Under the null, NQ, well, N is 100. 100 flips. If P is a half, then Q is a half. 100 times a half is 50. That's at least 5. Okay, so normal approximations are appropriate. So remember, if P is 1/2, it's good to know that Q is also 1/2 or 0.5. Okay, we compute the Z-Test Statistic. This is the given formula for the Z-Test Statistic. Now, the 0.5100, that's based on the sample, 51 heads and 100 flips. P hat is 0.5100. You can just put 0.51, but well, I said 4 sig figs just to be safe. I mentioned that because if you do some rounding in the bottom, for example, then maybe 4 sig figs. Okay. And then under the null, oh, let's write this in red. Okay, under the null, P under the null is 0.5. Remember, the null hypothesis says, way up here, the null hypothesis says P equals 1/2 or 0.5. All right, 0.5 right here. Make sure not to switch these, otherwise you'll get the wrong sign. Over, and remember, these are P and Q under the null, so it's the 0.5. Remember, this is usually the nicer number, right? So we're lucky it's the P, not the P hat. It's 0.5 times Q is 0.5 over, N is 100. You take the square root down there, work this all out, you get 0.20 to 2 decimal places. The Z-Test Statistic is 0.20. Now, right off the bat, without even doing p-values or all that, a z-score of 0.20, think about that. Does that mean that our sample results are that unusual? Again, think about it. The null hypothesis is saying the coin is fair. P is 1/2. We got 51 heads out of 100. Do you think we're going to reject the null? Use your common sense. No, probably not, right? Okay, note that a z-score of 0.20 seems very close to 0. See, if we had a z-score that was like above 2, especially way above 2 or less than -2, then we might suspect that the null might get rejected. Maybe, maybe not. But if your z-score is that close to 0, a 0.2, it's highly unlikely we're going to reject the null, just from our common statistical sense. The null, 0 here corresponds to the null. See, if we'd gotten exactly 50 heads out of 100, the z-score would have been 0, which would have perfectly reflected the null. Still, we would not have accepted the null, but a z-score of 0 would have been a perfect reflection of what the null was saying. A z-score of 0 means like you get 50 heads out of 100 flips. This is still pretty close. 51 heads out of 100 flips, we get 0.20 as our z-score. So it looks like getting 51 heads out of 100 flips seems to present little evidence against the null. If the z-score is 0, we'd have no evidence against the null. But even a 0.20, that's still little evidence against the null. Now, if the Z-score were like 20 or something, we'd have huge evidence against the null. Go straight to jail like in Monopoly. All right. Now that we have our Z-test statistic, we can now find the corresponding p-value. And of course, I'll give you relevant hints as necessary. In real life, you might go to Excel. So remember, the Z-score is 0.20, and it's a two-tailed test. So we need a two-tailed p-value. So we're going to mark off on this Z-bell, right? Well, the Z distribution corresponds to a normal bell curve. On the Z-axis, we're going to mark off the positive 0.20 and the negative 0.20. They're very close. I give you this hint that there's 0.4207 in both the left tail and the right tail. The two-tail p-value, or twice 0.4207, is 0.8414. Okay, so we're now going to decide whether or not to reject the null. Again, before I even show you, before we even get to there, right? Remember the idea. What's the threshold for what it means to be unusual? It is alpha, which is 0.05 here, the standard. When do we reject the null? When the p-value is low. If the p-value is low, the null must go. If the p-value is low, the null must go. Okay, wait a minute. 0.8414. You know, I don't really even have to look at your value for alpha. No one's alpha value is above 50% or 0.5. If your alpha value is above 0.5, then that means that you're shocked that a coin comes up heads. Okay, no one's alpha value is above 0.5. This two-tailed p-value, even the one-tailed p-value, but certainly the two-tailed p-value, this is massive. Over 84%. Come on. Whatever your alpha value is realistically, it's not going to be low. We now decide whether or not to reject the null. Okay, the p-value is 0.8414. Is it low? Is it less than alpha? No, it's greater than alpha. The p-value is not low. The p-value compared to alpha, the p-value is not low compared to alpha. It's way up here, way up there. The p-value is not low, we do not reject the null. Which satisfies our common sense, right? Because, again, the null said that the coin is fair. And if the coin comes up heads 51 times out of 100, well, no, we're not going to reject the null, not with any reasonable value for alpha. Okay. So now we're going to write our final conclusion relative to the claim. We do not reject the null. I'll put this in blue. We do not reject the null. Is that strong or weak? That's weak. That's weak. I sound like a teenager. Okay, that's weak. Okay, no offense to teenagers. We do not reject a null. That's weak. There is insufficient evidence. Okay, there's insufficient evidence to say such and such. Okay, there's insufficient evidence. What? What was the claim? The null was the claim. The null is the claim. So the null is on trial. How are we weighing evidence? We're weighing evidence against that claim, against that null claim, that the magician's coin is fair. That was the null. So again, the first part, remember, comes from the decision. Okay. The first part comes from decision. The second part comes from what the claim is. The claim. Which one was it? All right. Was the claim the null or the alternative? Conclusion. Let's put it all together. Mix and match. Conclusion. There is insufficient evidence against the claim that the magician's coin is fair. Let's read it through. Okay, think about it. The null says, or the claim is, right? The claim was that the coin was fair, remember? And it's good to indicate what the claim is. Okay, it's good to write claim. Okay, the null is the claim. The null claim is that the coin is fair. The null claim is that the coin is fair. Null claim is that the coin is fair. The coin came up heads 51 times out of 100. Well, since the null is a claim, we're weighing evidence against the claim. It's on trial. All right, we have this coin on trial. We have this coin on trial. The claim is that this coin is fair. Do we have enough evidence against that claim? All right, are we ready to say guilty? You flip the coin, grab that coin from the seat in the jury room, right? The witness stand, grab that coin, you flip it 100 times, it comes up heads 51 times. Are you going to have sufficient evidence against the claim that the coin's fair? If David says my coin's fair, are you going to say he's a liar? Probably not, right? There is insufficient evidence. There's not enough evidence against the claim that the magician's coin is fair. Now, the coin did come up heads 51 times, not 50 times out of 100. So there's some evidence, a teeny, tiny bit of evidence against the claim that the coin's fair, but it's insufficient. It's not enough. All right. And again, even though we don't reject the null, we never accept the null. Why not? Well, since p hat, our sample proportion, was 0.51, the most likely value for p wasn't 0.51, it was, the most likely value for p was not 0.50, which is what the null says, is 0.51, right? If p hat is 0.51, the most likely value for p is 0.51, not 0.50. And even if you had gotten 50 heads on 100 flips, right? Even if your p hat were 0.5 on the dot, again, p could have easily been, say, 0.51 or 0.49, and the 0.50 could have been the result of sampling error. So basically, when we don't reject the null, we're chalking things up to sampling error.
Right, so that was very sudden. Okay, any questions thus far? Any questions? I know I'm pushing the idea of the fair coin very hard, but I think that's a very good example to set up the playing field. Okay, it's a nice, comfortable place to start. Any questions? Any questions? Because trust me, they do these kinds of tests when they test for effectiveness of vaccines. That's what they're doing. They're doing tests for P, things like that. Any questions? We have a last video. It's about 18 minutes, and that'll finish us up. Okay, no rush. We still have some space if you have some questions, but any questions? Any questions? We have 18 minutes on this video, and then we might leave a little bit early. All right. Feel free to ask questions in the chat.
Hi, everyone. Let's do more with the magician's coin, some more tests. We want to test the claim that the magician's coin is fair at the 0.01 significance level. P is the probability of heads. The claim is that the coin is fair. Is that the null or the alternative? The claim is the null because coin is fair, P equals 0.5. The case of equality always goes with the null. And if the claim is the null, well, everything else is with the alternative. It's a two-tailed test. I'll do this in blue. The alternative tells us what kind of test it is. It's a two-tailed test. The alternative favors both low and high values for P. So we gather sample data. And let's say we get 63 heads in 100 flips. Now just think about that. The null claim says that the coin is fair. You see 63 heads and 100 flips. Well, think about it. So the sample proportion is p hat, 63 out of 100, 0.6300. We verify that normal approximations are appropriate. Both NP and NQ are at least 5, like before. Now the test statistic, well, the key difference is that the new sample proportion is 0.6300, which now pushes the z-score up to 2.60. See, before, when we saw 51 heads in 100 flips, very close to 50%, the z-score was 0.20, which was very close to 0, and we did not reject the null. But take a look at this Z-test statistic, 2.60. What do you think? That sounds pretty unusual. That's our hunch. But let's check, though. We now find the corresponding p-value. Now, it's a two-tailed test, so we have to combine the two areas in the two tails. I'm telling you there's 0.0047 in the left tail and also the right tail. So the two-tailed p-value will be twice 0.0047 or 0.0094. All right. Now, well, think about it, 0.0094. Right off the bat, that sounds pretty low, right? That sounds pretty low. It sounds like the null is likely to go. But when we decide whether or not to reject the null, yes, we do reject the null. The p-value is too low. When the p-value is low, the null must go. We do reject the null, but it's pretty close actually, right? Because alpha is 0.01, it's 1%, and the p-value is just a bit less than 1%. So actually, alpha was very open-minded towards the null. It was like someone who likes David. This judge is very lenient and almost lets David get away with this. But no, 63 heads out of 100, it's just barely too unusual. We reject the null. So is that a strong or weak conclusion? Is that a strong or weak result? We reject the null. If we reject the null, that's strong. That means there is sufficient evidence. What? Well, the null was the claim, so the null is on trial. So we're weighing evidence against that null claim. There is sufficient evidence against the claim. Conclusion? There is sufficient evidence against the claim that the magician's coin is fair. Which makes sense. I mean, if you think about it, 63 heads out of 100, your sense would probably be that, yeah, that's pretty strong evidence against the claim that the coin's fair. Although, again, it was a close call. The 1% was lenient. It almost let 63 heads get away with it. Next up. Here, we're going to test the claim that a magician's coin is biased towards heads. This no longer includes the case of equality. It's going to be the alternative as the claim. The claim will be the alternative hypothesis. A magician's coin is biased towards heads. So if the probability that the coin comes up heads is P, then the alternative claim here is saying that P is greater than 1/2. This indicates a bias towards heads. P is greater than 1/2. It is the claim according to the wording. And since this does not include the case of equality, it's the alternative hypothesis. Now, the null hypothesis, again, we live in a world where either the null or the alternative is true. Technically, the null hypothesis would say that P is less than or equal to 1/2. But again, and you could write that down. You could write that the null says that P is less than or equal to 1/2. But by convention, we normally replace this symbol with just a simple equal sign. Alpha is 0.10, significance level. And it's a right-tailed test because this alternative favors the right tail. It favors higher values for P. Again, P is greater than 1/2. It corresponds to the alternative, not the null, because this does not include the case of equality. The case of equality always goes with the null. The case of equality always goes with the null. This has to be the alternative. All right. Again, it's a right-tailed test because the alternative favors the right tail for P, greater values. Okay, now, finally, we gather the sample data. Remember, you're supposed to do this after the setup. This time, the coin is flipped 100 times and it comes up heads 60 times. 60 out of 100. Our sample proportion, P hat, is 0.6000. Verify that normal approximations are appropriate. NP is at least 5, like before. Again, the only thing that's different from previous examples in this Z-Test statistic is that we changed that upper left value. It's now 0.6000. The Z-Test statistic is, look at this, exactly 2.00. Well, it's hard to say. It's right, kind of borderline, right? You may not have a hunch. It really depends on alpha. We now find the corresponding p-value. Okay, this is a right-tailed test. Remember, it's a right-tailed test. The alternative favors the right tail, greater values for p. It's a right-tailed test, so we need a right-tailed p-value. And I'll tell you that to the right of z equals 2, it's 0.0228. The right-tailed p-value is about 0.0228. So we now decide whether or not to reject the null. Well, what's the threshold? It's alpha. Alpha was 10% here. Alpha is 0.10. The p-value is 0.0228. Is the p-value low or not low? Is it less than alpha or greater than alpha? This is about 2%. This is 10%. The p-value is less than alpha. The p-value is low. The null must go away. We reject the null. And by the way, it was kind of a close call, right? I mean, z equals 2. Well, it really depends on what alpha is, right? Okay, we reject the null. Finally, we write our conclusion relative to the claim. We reject the null. Is that strong or weak? That is strong. There is sufficient evidence. Sufficient evidence of what? What was the claim? The alternative was the claim. So remember, the idea is that the alternative is like the research hypothesis. Can we prove that this drug works? Can we prove H1, the alternative claim? You're weighing evidence for the alternative claim. You're wondering if the drug works for the claim that, the magician's coin is biased towards heads. Remember, the coin came up heads 60 times out of 100. There is sufficient evidence for the claim that the magician's coin is biased towards heads. So the 60 heads, biased enough. Well, the results are biased enough. The sample results are biased enough. So we're concluding that, hey, there's sufficient evidence that, in fact, the coin is biased towards heads. Now, you might be going, well, wait a minute. Here with 60 out of 100, here with 60 out of 100 heads, we rejected the null and said that there was a bias. Okay. It is pretty clear. Here with 63 heads, we just barely rejected the null. In both cases, we rejected the null, but here we just barely rejected the null. Why was it so close here? Well, a couple of things. For one thing, it's a two-tailed test that contributes, but also alpha was very tight. It was only 1%. So sometimes when you look at 60 out of 100, 63 out of 100, it's hard to guess which way it goes. You have to work it out. It's not like 51 heads where you're clearly not going to reject the null, or 99 heads where you clearly are. All right. In our last example, right? Yeah, in our last example, all right. We want to test the claim that a magician's coin is biased towards tails. Biased towards tails. Now, if P is still the probability the coin comes up heads, then if the coin is biased towards tails, that means P is less than 1/2. That's our claim. And because it does not include the case of equality, it goes with the alternative. The null technically says that P is greater than or equal to 1/2, but again, we usually write just equals. Alpha equals 0.05, which is standard. And it's a left tail test because, well, I'll do this in turquoise. It's a left tail test because the alternative favors lower values of P, lesser values of P. So basically, if we reject the null in favor of the alternative, we have to have strong enough evidence that the coin is biased towards tails. We now gather sample data. 60 out of 100 this time. 60 heads out of 100 flips. P hat is 0.6000. Well, wait, hold on, wait. Before we go on computing things, hold on. We got 60 heads out of 100 flips? Wait, the claim is that the coin is biased towards tails, not heads. Is there any way that we're going to reject this null in favor of the alternative? No way. There is no way it's going to happen. You don't have to do any more computation, really. Just from statistical sense, you realize, wait, there's no way I'm going to dump the null in favor of a tail alternative, a tail-favored alternative, when I'm getting more heads. So based on the sample data, there's no evidence for the claim of a bias towards tails. The sample data is running away from the alternative. The sample data is running towards heads. Whereas the alternative, so the sample is running towards more heads, 60 heads out of 100, but the alternative is going in the direction of tails. There's no way dumping the null. There's no way. If anything, there's a bias towards heads. It should be clear at this point, if you use your statistical sense, that the null will not be rejected in favor of the alternative. But if you were to continue working it out, and I may have you work it out in further detail, I could have you work it all out mechanically. Again, verify that the normal approximations work out. Yes, NP and NQ are at least 5. We've seen that many times before. For the Z-Test Statistic, it's the same expression that we had earlier. Again, we have 60 heads out of 100. So the Z-score is still 2.00. But what do we do this time? Let's see. Let's find the corresponding p-value. It's a left-tailed test. Wait, so when I draw 2 on the z-axis here, it's a left-tailed test. I need a left-tailed p-value, which means I get all of this, all of that. And you're going, well, that's kind of ridiculous, right? Yeah, it is. The area here, the probability is 0.9772. That's your left-tailed p-value. This is your p-value. Is there any way whatsoever that p-value is low? Is there any way that p-value is low? There's no way. Again, it makes no sense for your alpha to be 0.5 or higher, right? There's no way that alpha is going to be 0.99. Decide whether or not to reject the null. Let's see. Almost 98% versus 5%. What do you think? Almost 98%. I think that's higher, right? It's not low. The p-value is not low by any reasonable measure for alpha. We do not reject the null. But we should have been able to figure that out early on. There's no way we're rejecting the null in favor of the alternative. So what can we say? If we do not reject the null, is that strong or weak? Is that a strong result or a weak result? That's weak. That's kind of like, not guilty or the thing. We're not sure if it really works. So we do not reject the null. We do not reject the null. It's a weak result. So there's insufficient evidence of what? Okay. What's the claim? We have to ask now, what's the claim? Remember, the beginning of your sentence starts with the decision. Do you reject the null or not? The end of your sentence deals with which is the claim. Here, the alternative was the claim. It depended on the wording of the problem. Here, the alternative was the claim. And we're wondering, can we prove the alternative? Is the research hypothesis. If the claim is the alternative hypothesis, then is the research hypothesis. Can we prove it? We're weighing evidence for the claim, that yada, yada, yada. So altogether, there is insufficient evidence. There's not enough evidence for or in support of the claim that the magician's coin is biased towards tails, which makes total sense because the sample is biased towards heads. The sample is biased towards heads. But the alternative was pointing towards tails. So there's no evidence. There's insufficient evidence. There's no evidence. It's going in the opposite direction. There is insufficient evidence for the claim that the magician's coin is biased towards tail. It's like asking your friend, so this guy that you're setting me up with, right? Or this gal that you're setting me up with, is this person a terrible, mean person? Is this person a terrible, mean person? Am I going to dislike this person? And this person goes, your friend goes, oh, well, this person saves kitty cats from trees, and he's going to cure coronavirus. And let's see, is he a bad person? Let's see. Well, of course he's not a bad person. Like, well, at least based on that. If the sample's going the wrong way, you're not going to reject the null in favor of the alternative. All right. If the alternative is a claim. Next up, test for other population parameters.
That's going to be for later. Okay, so today these were lessons 33 and 34, right? So we're basically doing an introduction to hypothesis testing, starting with test for P, which is convenient because we can talk about coins. But when they talk about this deal of efficacy, right? They're dealing with proportions when they're dealing with the efficacy of these coronavirus vaccines. So they really are doing test for P, right? I can't wait to get hold of those articles, as I've said. All right, so let's see, it's 9:27 now. That was all I had. Okay, we're going to continue with tests for other parameters next time. Look at this. We have plenty to do next time. All right, 4 lessons next time. I do encourage you to do the homework for 33 and 34 by next time. I'll continue to grade the homework 3s, right? And then later the 4s. Okay, any general questions? Any general questions? Well, otherwise, we'll have a good couple of days. Okay, but I will stick around until 9:35. I'll keep the chat open. Okay, so you should have gotten an email for both homeworks 1 and 2. So far I've graded 1 and 2, and you should have gotten the reports for those. I'm still grading 3 and 4. Okay, so 3 I hope to be done within a week or so. Okay, and maybe 4 in here as well. We'll see. All right. Okay, but I do have the grades for the first 2. So yeah, if you don't have your grade reports for the first 2, email me and I can tell you your grade reports for the first 2. 3 I'm still working on. Okay, and 4, yeah. That if I were caught up, I would have done 4, but I'm not caught up. Sorry. To be honest, during Thanksgiving week, there was a tough pre-calculus homework I was grading, and that took a lot of my time last week, actually. Yeah. Okay, so I'll stick around until 9:35 if you have questions. All right, I'll stick around. Otherwise, I'll close the session 9:35, but I will stick around. Okay, in fact, at this time, I'll go ahead and pause the recording.